now this graph we have discussed yesterday. So any doubt, because Sumon was asking yesterday, sir, if you could repeat this discussion. So that's why I thought, okay, let me discuss this. Okay,
Yes, sir.
if you see the wettability index 0, 0 means it's a neutral wettability. If you have a positive value means you have a water weight, and negative,
Water weight.
yeah, a negative wettability index means
Oil weight.
Oil weight.
So very simple thing is, when particularly during migration, okay, when you have a migration of oil into the reservoir, what is happening? If you have a water weight, then generally the oil could not displace the water which is the superficial water, as well as the water occupied the small pores that could not be knocked out by the migrating oil. So that's why initial water saturation in case of water weight is more, whereas in oil weight reservoir, because oil weight reservoir means oil, there is a preference of oil to enter into the rock surfaces. So that's why oil during migration, oil will enter into the pore space and they displace the water which occupied the pore space. That's why if you see the connate water saturation in case of oil weight is generally less. That's why if you see the graph in the left panel, minus wettability index, you see the initial water saturation is less. Whereas if you go towards the right side, the top part, even the high water saturation, I mean 30, 40, 50% water saturation also we could see in some cases. So that's why this is the initial part. Okay. So now in the right panel is you have wettability index as well as the residual oil saturation, and in right side, if you see, it is your oil recovery. So what is happening, because this is initial condition and this is when you are producing from it. Okay. So if you see residual oil saturation is less in neutral weight when it is 0, the value of wettability index, and oil recovery is maximum. Whereas in the weighting rock, that means even if it is oil weight or water weight, strongly oil weight or strongly water weight, will get less recovery. Why it is so? Can anybody visualize what is happening? So it's not, needless to say, when you have water weight, water is staying more in the rock surfaces, isn't it? And what is happening, the oil, as it is non-weighting phase, it will occupy the middle of the pore space. So that's why if we consider each and every pores are rock surfaces surrounded by water and oil droplets are occupying the middle of the pore space, that means lot more oil would be unrecovered. Okay, so that's why the volume of oil is staying into the reservoir, even if it is strong water weight will be more. And the reverse is very simple. If it is oil weight rock, then superficial oil would be always there, so we could not recover more. So that is how in both the cases, oil weight or water weight, the recovery both the cases is less. But if it is neutral weight, so what is going to happen? There is no preference of the rock surface, either oil or water. So that's why what is happening, if you see the oil which are isolated in the reservoir, they can displace the water and connect together to make a continuous film, and accordingly we could produce more. So that is how this is very important to understand, in particularly in terms of the physical behavior, what is happening. Okay. So any doubt so far in this?
No, sir.
Yes, sir.
Very good. So now we are going to the capillary pressure. So capillary pressure means if you have a small size, if you see, because capillary pressure play an important role for relative permeability. Okay, so interfacial tension, wettability, capillary pressure, all will actually dictate the saturation of water and oil within the reservoir, and that dictates our relative permeability graph. Okay, so that is how we need to know what is the capillary action. So this is what in 10+2 level, hopefully we have discussed, you have studied this. So in a capillary tube, you see, due to the adhesion tension or surface tension, the fluid will be rising up, okay, and the gravity will try to pull down. So due to this adhesion tension, actually, depending on the size of the capillary tube or maybe the material, the height will be different, and that is, one is wettability and another is capillarity. Okay, so that's why if I just give you a formulation, the force balance, by an downward force and upward force. What is the downward force is the gravity, and upward force is
Hmm.
tension or
Oh, I see.
okay. So if you just balance it, then you will get the capillary pressure is related to the adhesion tension as well as contact angle and the radius of the capillary tube. Okay, so that the same formulations we can use to understand if you have a small area having small pores and an area having bigger pores with the same material. So if you see that we have two panels here, one panel having liquid and the theta is same. Okay, theta same means the material by which the capillary or maybe tube are formed is same. That means the rock materials are same. If I say, okay, theta angle is same. So that's why if you see the smaller the capillarity, the bigger the rise of the fluid or liquid. Okay, and in the right case, your capillarity, your diameter is more. That's why your rise of the water is not more. So how it is related? And the second part, if you see the contact angle are different. That means we have the same radius of the pores or maybe the capillary tube, but the materials are different. The contact angle, this theta and this theta are different. Okay, so that's why what is happening when we are discussing about the reservoir situation in terms of water zone, transition zone, and oil zone, then we need to consider this part. What is the that means we need to think about the size of the pores present in the rock. Number one. Number two is because if you just see these formulations, the formulation is PC 2 sigma Al cos theta Al by R. A means air, L is liquid. If we just change it, because PC is what? PC is rho GH, isn't it? Or you can say here del rho. Del rho. So if I just put my rho in the left side or maybe H in the left side, so it would be actually what? It would be 2 sigma cos theta L by del rho G into R. That means the height of the transition zone is very much dependent on parameters which are 2 sigma cos theta in the it is directly proportional to how cos theta value changes. Cos theta value changes from 0 to 90 degree. It is from 1 to 0, isn't it? So that means depending on the theta value, the cos theta value is changing. It's an inverse way. If theta is less, your cos theta value is more. If theta angle is more, then cos theta value is less. So that's why the height of the transition zone is very much related to the wettability. Then in the lower part, if I change the PC means rho GH, so H would be inversely proportional to del rho and inversely proportional to R. R means if your diameter is less, height will be more. If your diameter is bigger, then height of the transition zone will be less. So following the same understanding, what you can see, and also this part also capillarity is important consideration. So this is history. History means how a pores is occupied by the fluid. Are we taking the fluid out from the pores or we are injecting the fluid inside the pore? So two parameters are important to understand here, because when a reservoir is filled up or reservoir pores are occupying by the migrating hydrocarbon fluid, that time it is an advancing contact angle. But when we are trying to take it out from the same materials, that will be a different nature. So that's why one case is imbibition and another case is the drainage. If you remember imbibition and drainage terminology, let me ask you, what is imbibition? Ali, imbibition, the process. Imbibition, Ali, is it audible? Two terminology we discussed now. One is imbibition and another is drainage. Okay, so what is imbibition and what is drainage? When we are displacing a wetting phase with the help of a non-wetting phase, drainage, isn't it? And when we are displacing a non-wetting phase with the help of an wetting phase, that is called imbibition. Imbibition. Okay, this is a very important terminology in reservoir engineering. So this is a must. Even any interview, people can ask you this question. What is imbibition? This is a very important part. Okay, so that's why once you just go to this go to this part, let's say this part. So this is one part which is very important. Hopefully, during your study in the petroleum geology, you have seen this diagram, isn't it? How the crude oil is migrating and occupying the reservoir pores. Okay, so we have relations with capillarity. So what is happening? You see, depending on the size. Now you try to visualize how actually crude oil occupied in the reservoir in different places. So what? It's an inhomogeneous reservoir. In inhomogeneous reservoir, what is happening? If you see, in some cases, your particularly, just try to visualize, because you see the reservoir is inhomogeneous in nature in terms of mineralogy. Number one. Number two, size of the pores. Okay, and number three is actually the your size of the pores and number of crude oil. Okay. Now, when the crude oil is migrating to the place of reservoir, what is happening? Let's say small pores. What is
The
going?
capillary pressure, sir.
Yes.
Capillary pressure.
Yeah, capillary pressure. So if it is a small pores, then it would never be occupied, isn't it? Because
Yes, sir.
oil could not displace the inside water. Why? Because
Yes,
if you see the A, B, C, D formulations, this formulation could not satisfy. Okay, that's why the crude oil could not enter into the small pores. Okay,
yes, sir.
if the bigger pores are there, then definitely crude oil will enter. Now another part will play a role, wettability. If the pores are water weight in nature, they will the oil will prefer to enter into the pores, so that's why they will occupy. But if it is water weight, generally they will not. So that means what is happening, depending on the mineralogy present into the reservoir, number one. Second, their wettability nature. Third one is the size of the pores, and fourth one is the type of crude oil. Because we discussed about the crude oil composition, it's a saturate, aromatic, resin, and asphaltene. All the compositions are actually polar. Not all, few components are polar in nature, and the surface property of the minerals are different in nature. Okay, that's why they will adsorb on the rock surface differently. So that's why different parameters in molecular level actually control how the pores will be occupied by different fluids in the initial stage of migration. Okay, so have you understood this part? So
Yes.
that means in a reservoir, the distribution of initial fluid saturation or fluid distribution is not same. That would be guided by type of the minerals present in the pores or the pore lining. Second one is your size of the pores. Third one is the capillarity of the pore channels or the pore neck, or maybe because of pore throats. And fourth one is the type of the crude oil present in this reservoir. Okay, so that is how your whole reservoir is distributed, and you need to understand this. It is not mathematics. You need to understand by considering each and every parameters one by one, and then you have to visualize what is my present reservoir situation. Okay, so agreed? Understood
Yes,
this
sir.
part? Okay, so that means
Yes, sir.
it is not that a well very closely spaced, one well is producing very nicely, another well is not producing equally. So now you need to visualize this production of a well right from its different parameters. It is not that okay, they are closely spaced means they could produce the same amount of crude oil on, okay, so that is not always. So next part is your saturation. Okay, so how we understand the saturation part? How we get the saturation? Okay, so this is the distribution pattern. Okay, so I'll just how we measure the saturation in a reservoir. One is sometimes,
Connate water.
yeah, not connate water. So you see, we could collect a core plug samples and try to saturate it and desaturate it, isn't it? So that is one part way of looking the things. And if you remember, whenever we discuss the capillary pressure versus saturation, we correlate the core plug data into the actual depth correlation, isn't it? Some relations we have discussed the pattern. So today I'm not discussing that because we have already discussed this part. So I'm trying to give you the overall idea of the information of the petrophysics. Okay, so once we get this idea, so you can see this distribution pattern. So what is it? This graph, capillary pressure
Pore
versus
throat
saturation.
distribution.
Yes, pore
Pore
throat
throat.
pore throat distribution. That means if we inject either non-wetting phase, mainly we use mercury for understanding the capillary pressure, but mercury is now in carcinogenic, so now people are using differently. Sometimes they are giving certain non-wetting liquid also, but still mercury saturation is going on. Okay, so if you see the shape of this capillary pressure graph, you can understand. So initial, here we have three graphs, isn't it?
Yeah.
Okay, so in the lower part it is 100% saturation with water. Then once you try to inject mercury into the core plug, you see, depending on the type or the distribution pattern of your pores, they will saturate and the capillary pressure will change, isn't it? So if it is, let's say in the first case, let's say in the graph B, if we see a graph, actually if you see the saturation is more or less same, increasing without any change in the capillary pressure, and after that it is asymptotic or is a vertical, isn't it? So what are the parameters we are getting out of from here? The pore size distribution within the core plug samples. Yes, it's a large pores and the very well sorted, because if you see more or less 70-80% saturation is done in a single capillary pressure. So that's why more or less size of the pores are very homogeneously distributed. Okay, so but if you see the lower part, lower graph, you see incremental increase in capillary pressure will only increase slight saturation. So that's why the pore size are very homogeneous in nature and there's a poorly sorted. And if you see the asymptotic point where the graphs is more or less vertical, that is the coned water saturation. Why it is coned water saturation? Means even if you increase pressure, you cannot increase the saturation. That means the rest of the part is occupied with water. That's why we could not increase the saturation of the non-wetting injection fluids. Okay, so that is how. And how we calculate, you know that how we calculate, I discussed. So you distribute your x-axis into different values, 100%, 50%, 75, 25%, and capillary pressure. So if you just get the formula pore threshold sorting, square root of or
quartile of
uh,
rank 1 and rank 3.
yeah, rank 1 means your 75% and 25%,
Yes.
isn't it?
25%.
Yeah.
Yes.
If capillary pressure is same for this 2% of saturation, then obviously it is 1. That means the core plug is very well sorted. Okay.
Well sorted.
Yes. So this is what is important. Okay. So now this use of capillary pressure. So you just see, determine a fluid distribution reservoir. I discussed you how this core plug data is related to your depth correlations. If you remember, some formulations are there in your all units. If you just go back to your book again, you can correlate it. Okay. Determine the residual oil saturation for water flooding applications. Then determine pore size distribution index. May help in identifying zones of or rock types. Input for reservoir simulation calculations. Okay, so this is what are the important. So this diagram is very clear to you now. Okay, so if you see initially, so what is called threshold pressure? Do you know what is threshold pressure? The pressure at which we start the injection into the core plug, that is called threshold pressure. It is not always 0. Sometimes it is 0, sometimes it is less than 0 also, means automatically we can introduce. So that means when we can introduce in the very easy way, that means the bigger size pores is very big. We can easily introduce mercury into the core plug sample. So that this graph is generally utilized in most of the cases to understand the pore size distribution pattern as well as the correlations. Okay. So any doubt on this graph?
No.
Suman?
No, sir.
No, it's clear. Ali? Ali, is it okay?
Okay, sir.
Okay,
Yes.
fine. So now this part. So now if I put this graph and ask you in three different zones, what is the production profile of if I perforate in oil zone, transition zone, and this part is clear to you, the formulations. I didn't put purposefully the formulations here. So what, by just observing the capillary pressure graph, we could easily visualize what is the saturation level in the whole reservoir. Okay, so if you see the oil page or we can write go from below. So there is two terminology. One is free water level and another is oil water contact. Can you tell me what is the difference between oil water contact and free water level? Anybody? Are they same or there is some difference?
Difference.
Yeah, difference. What is the difference?
Uh,
The surface activity. Surface means if your water weight or oil weight surface, that means even if you have a 100% saturation, they will not start flowing from your reservoir. Okay, so that's why free water level means when they are free to move. Okay, so if you see sometimes a full of glass of water, even the water is gone up to the margin of the glass, water is not flowing, isn't it? So that is actually the surface property. Okay, that is surface property. That's why free water level is slightly below the oil water contact. Okay, oil water contact is defined as 100% saturation, but free water level is not 100%, it's more than 100% saturation, then that time they will start. Okay, so that's why you see the then you see, depending on your type of crude oil and or maybe type of your rock property and fluid property, fluid means pair of fluid property, your this capillary graph changes. Okay, this capillary graph. Okay, so this, we have discussed depending on what are the parameters involved for making this transition zone. Just now we discussed the mathematics. H equal to 2 sigma cos theta divided by del rho, del rho G and R. Okay, so that means this graph or maybe transition zone is very much dependent on the rock and fluid property. If the contrast of the density between two fluids, water and oil, is very much high, then transition zone will be very short. If your pore size is very small, your transition zone will be very big or height will be more. And if you have water weight rock, then water will, that means that also water will continue to go up to a certain level. Okay, so that is how, depending on the type of crude oil, depending on the type of the water, depending on the type of the mineral present into your, so that's why if I ask you a question here, throughout the reservoir, is the oil water contact zone is same or it varies? The oil water contact is 100% saturation of water, isn't it? Where the 100% saturation ends and the oil saturation is going to increase as you go up, isn't it? So now if you follow this formula and the relationship between oil water contact and the rock type or mineralogy of the rocks as well as the size of the pores, are, so my question is oil water contact is in the same depth of a reservoir or it will vary? It will vary.
Sir, repeat. Very.
Why vary? Because you see, each and every point the reservoirs are not similar in nature, isn't it? Somewhere you may have a sandstone grain, somewhere you may have the carbonate mineralogy, sometimes your matrix are different, the pore size are different. Even if you have the same crude and water below, your transition zone will not same. So that's why the important part, it is not a paper-like structure, okay, oil water contact is in the same depth. It generally varies in the whole reservoir. That's why when we are planning for development activity, I should be careful enough to understand how the oil water contact varies throughout my reservoir. Okay? Okay, so now the relative permeability graph. Relative permeability, I'll just directly go to the relative permeability graph. So these are the definitions. Okay, so you have effective permeability, you have absolute permeability, and you have relative permeability. So relative permeability is nothing but ratio between effective and the absolute. Okay, so absolute. So now if you just go through this three part, water phase, oil phase, and gas phase, you see where the water will be occupied. Try to visualize, this is very important part. I have told you earlier during the migration also as well as, so what water phase, what if your rock is water weight, water will be occupied in the smaller pores. Are you agreeing or not? Because this water is not displaced right from the beginning of the oil migration. Is it clear? Yes. And relative permeability, what is happening, if it is the rock is water weight, they will occupy the surface of the big pores also. So how your water would be there? Water will be occupying the small pores of the reservoir as well as the surface of the rock grains if it is water weight. Okay. Now oil phase. Oil is located between water and gas because gas is non-weighting phase. That's why it will always occupy the central position of the pores. Okay. So it would occupy the central position of the pores, and if it is water weight, water will occupy the grain surfaces. So oil will occupy in between. Oil will occupy in between. Okay. So that's why when we are discussing the permeability, you see relative permeability of water to water is a function of water saturation only. Why it is so? And gas permeability is the function of only gas saturation, whereas oil permeability is function of both, all three, oil, water and gas saturations only.
Because it is in between the
Yes, so that means
and gas.
Gas will be flowing when the central position of the each and every pores are occupied by gas and they make a continuous phase, isn't it? So gas saturation will dictate the gas flow, water saturation will dictate the water flow, and but the oil saturation cannot dictate the oil flow. It is by contributing of all the saturation together. Okay, so this is what is happening. So now if you visualize when actually we are taking the production, all the parameters you need to take care, otherwise you cannot really plan for your production. Because you see, this is what you need to understand, because petrophysics will guide you. If I have drilled two wells very near places, but they are not producing same volume, so you need to get the idea from this information only. So what are the parameters which controls my flow into the subsurface reservoir? Okay, so now if you see water related permeability, so what is left side? If you see this graph very carefully, okay, so that means so this left side part, that means below level of your connected water saturation, this is actually the zone which is what? Clean oil zone, isn't it? That means in reservoir, in the oil reservoir itself, where you have the oil saturation and the connected water saturation. So if you perforate this area, what you will get?
Oil.
Only oil, clean oil. Okay. Now in the right side, you have residual oil saturation and you have your KRW. So okay, so this is the which situation? Below WC. Am I correct?
Yes.
Below oil water contact, because below that the oil saturation is 100%. No, sorry, water saturation is 100%. That's why, okay, so 100%. So that's why only in that case will produce only the oil. Okay, now water. And in between, hello? 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 Am I audible? Am I audible?
No, sir.
Yes or no?
No.
Yeah, okay. You are not in connection in my ear actually, but other Ali, is it audible? I'm audible? Suman?
Yes, sir. Yes, sir.
Yeah. So actually, yeah. So now if you see this graph, it is very clear. If we are in the transition zone, then we'll produce either both oil and water together. In the left side, it is the clean oil zone, and right side is water zone. Okay?
Water zone.
Yes, sir.
Okay. So what is happening with time? So we discussed about the reservoir drive mechanism. So once we start taking production of the clean oil zone, okay, so what is going to happen? The water saturation will increase automatically.
Water saturation, yes, sir.
That means what is happening? The transition zone
Water.
will go up. Tell me.
go up, transition zone go up, and water push the crude oil to.
Yes. So that
Uh,
means what is happening actually, if you just visualize the pores, each and every pores now will be changing their saturation. Water will increase, oil will decrease, and that's why the relative permeability values will be changing depending on the saturation of oil and water, and will gradually get the production value changes with time. Okay, so agreed. So this is inevitable. You cannot change this value. It is, but we try to restrict the value. That means we could reduce it by doing our different activity. So that is
yes,
happening.
sir.
Okay, so in case of uh, so you see here the things are different. In gas, that means if we discussed about the water zone, transition zone, then we oil zone, then oil gas transition zone and gas zone. Okay, so if you just see this, if you just see here, you can understand here it's a total, in the x-axis a total liquid saturation. Why it is not water saturation? Anybody? You see it's a total liquid saturation. And in this case, we
Because it
have
is.
water and gas saturation together.
Hmm. Yes.
Okay, so that's why it is total liquid saturation. Sometimes we may get a little bit of liquid also. So that's why oil, in case of gas and oil permeability case, we have all three parameters, because gas saturation is there, oil saturation is there, as well as we have the connate water saturation. That's why x-axis, if you see this previous graph, here we have the water saturation only in the x-axis. Okay, but in this case, if you see in the below part, we have the total liquid saturation. So there is a difference. Take care of this part when you are discussing, because if somebody asks you why this is not water saturation, it is only, that means this case we have total liquid saturation in the pore volume, and that dictates our oil and gas flow. Okay, so now factors affecting relative permeability, now it is clear to you. Fluid saturation, geometry of the rock pores, rock wettability, because each and every graph we discussed earlier, and fluid saturation history. That means it is an this imbibition process is happening or the drainage process happening, because both the cases, even if you have the same pressure, your end saturation would be different. That I have discussed in the earlier diagram. If you see the bottleneck diagram, two bottle example. Okay, so uh, this diagram. So in both the cases, you see your capillary pressure is x psi. One case we are displacing wetting phase with the help of a non-wetting phase. In another case, we are injecting a non-wetting phase. Okay, so you see the x psi initial case is 90-10 and the second case is 20-80. So that is the end. That means same situation, but in one case we are doing the imbibition process, another case we are doing the drainage process. So that is how things are happening. So these are few things which you need to take care when we are discussing our particular part. Okay, so now, okay, so now you see when you are predicting wettability, how wettability plays a role in your flow. So even if you consider 50-50 saturation, you see in strongly water weight and strongly oil weight rock, the flow behavior would be different. So that means these are important informations when you are working as a professional. You should take care of this part. Even both the cases, one say you see in case of the left side, strongly water saturation, water weight rock, you see 50% saturation. You see the water permeability is very less compared to oil. But if you see the right side graph, 50% saturation, more or less same. So that's why when we are predicting flow with time, we should be careful enough to understand the small pores and big pores. You see how the graphs will be shifting, because in case of small pores, you see the residual oil saturation and connate water saturation would be higher. What we discussed in the very first slide today, isn't it? Small pores, because from the beginning the zones are full of water. Initial water saturation is more. That's why connate water saturation is more. So that's why if you see the arrows are towards the central side. That means residual oil saturation as well as the water saturation is more. Whereas in bigger pores, we could take out maximum from it, and the initial saturation will be also less. So that's why these are some of the particular things we need to take care when we are considering the reservoir flow. Okay, so production behavior I have already discussed, isn't it? So oil, if you perforate in oil pay zone, if you perforate in transition zone, and if you perforate, okay. So now drainage and elevation, you see the two graphs are different, isn't it? That means in the same system, if we study drainage and if we study imbibition, so there is a different graph, and the saturation in the same capillary pressures will be different. Okay, so this is what. So this is a drainage graph and imbibition graph, very important. So this is, in different cases we need to consider which situation, and accordingly we have to use, either we are using the drainage graph or the imbibition graph. Okay, so now why it is important? Because whenever you are planning for the production history, it should be we should be very cautious about understanding all the things together. Okay, so now these are already known to you, isn't it? How this distribution pattern, their saturation changes. Okay, so now these are few questions I actually put. Okay, the diagrams. If I just put this diagram and ask you how you are evaluating your reservoir, which reservoir is good, which reservoir is bad in terms of production performance, these graphs only, left side. Okay, different formations are there and graphs are there. Okay, so that actually these are the few graphs I discussed in the last semester, last semester also, first semester, different graphs. How this, because capillary pressure plays an important role for permeability determination. Okay, and saturation value. So are you clear with all the parts of why petrophysics and fluid property is important for doing the development geology? Okay, any question, Ali? Any doubt so far?
No, sir. Can you send us this PPT?
I have already this PPT. You don't have this PPT? You don't have this PPT, or yes?
Yes, sir. We don't have this and the previous one.
I sent you hopefully all 58 of my. I given you in the last semester all 58, if you remember. 54.
Okay,
Not
sir,
sir,
so this is
58.
included in
Sir,
that.
49, not 58.
Oh, 50 hopefully. It is there. It is there. You just check it. All are there. If not, I will send you. If you just send me in WhatsApp new message, okay, sir, we have the all the PPTs. It is there.
Okay.
Okay,
Okay,
if
sir,
not, I will
okay.
send you. Okay, okay. Hopefully, it will
Okay.
just 40 minutes is over. It will automatically cut. Suman, any questions? So, how it is your area now is fine?
Sir, yesterday night, one case, new cases come first.
Ah, so take care.
So first time in Tripura.
Oh, please take care. Huh?
Yes, sir.
Okay, take care and bye for today.
Bye,
Tomorrow,
sir. Thank you, sir.
okay, tomorrow you have one classes with a new idea. You just check it and